Modern commercial jet engines are among the most refined pieces of engineering ever developed. They are quieter, more fuel-efficient, and dramatically cleaner than the engines that powered earlier generations of airliners. So in this video, we take a look at why Boeing introduced engine chevrons, how they reduce noise, why they also reduce engine efficiency, why Airbus refused to adopt the technology, and why Boeing itself eventually decided to abandon the design on its newest aircraft. And be sure to check out Simpleflying's flight tracker. From live alerts and data on commercial, military, and government flights, it goes way beyond your standard tracker. It was built specifically for avgeeks, free and live, right at your fingertips. Chevrons are serrated trailing edges built into the rear section of an engine nozzle. Boeing introduced the technology commercially on the 787 before expanding it to the 747-8 and the 737 MAX family. Every 787 engine variant uses chevrons regardless of whether the aircraft is powered by Rolls-Royce Trent 1000s or General Electric GE NX engines. The 747-8 and all 737 MAX variants also feature this design. The engineering principle behind chevrons is relatively straightforward. Modern turbofan engines produce two separate exhaust flows, a hot, high-velocity core stream from the combustion section and a cooler bypass airflow generated by the fan. The interaction between these two flows creates turbulence, which is a major source of jet engine noise. Chevrons reduce that turbulence by generating controlled vortices that mix the exhaust streams together more gradually. The smoother transition lowers the acoustic intensity of the exhaust plume, particularly during high-thrust operations such as takeoff and initial climb. The concept emerged during a period when airport noise regulations were becoming increasingly restrictive worldwide. Airlines operating large fleets at densely populated urban airports faced growing pressure to reduce community noise exposure. Boeing saw chevrons as a way to improve compliance without fundamentally redesigning engine architecture. Yet the aerodynamic realities behind the design created complications that became increasingly apparent over time. The central problem with chevrons is that the vortices they intentionally create do not simply disappear once the aircraft leaves the airport environment. The aerodynamic mixing process continues throughout the entire flight, including cruise conditions where noise reduction is far less important. Those vortices slightly disrupt the exhaust flow and increase drag, which reduces overall engine efficiency and marginally lowers thrust output. Aviation analyst Peter Hornfeld, better known through Mentor Pilot, has estimated that the thrust penalty from chevrons is approximately 0.5%. While that figure appears small, aviation economics are built around extremely thin performance margins, where even fractional efficiency losses matter significantly. For high-utilization aircraft such as the 737 MAX, the effect becomes cumulative. Narrow-body airliners often perform multiple short-haul sectors daily, so a minor efficiency penalty applied continuously across thousands of annual flights translates into meaningful fuel burn increases over the lifespan of the aircraft. This creates the core engineering contradiction behind chevrons. The system addresses a problem most critical during takeoff and landing, but imposes its aerodynamic penalty continuously. The issue becomes especially relevant during cruise flight. At high altitude, engines operate in carefully optimized conditions designed to minimize drag and maximize fuel efficiency. One of the most revealing aspects of the story is that Airbus never adopted the technology on any of its competing modern aircraft programs. The European manufacturer chose an entirely different path for noise reduction, relying instead on nacelle acoustic treatments, advanced fan designs, and high bypass ratio engines. Initially, Boeing's patented chevron design prevented competitors from using the concept commercially. That patent protection remained in place until 2021. However, even after the patent expired, Airbus still showed no interest in integrating chevrons into aircraft such as the Airbus A350 or Airbus A320neo family. The company's reasoning was unusually direct. A350 chief engineer Dougie Hunter publicly explained that Airbus found no compelling advantage in the technology. According to Hunter, Airbus engineers determined that chevrons did not provide sufficient noise benefits to justify the associated specific fuel consumption penalty. That statement highlights an important philosophical difference between Boeing and Airbus during the development of next-generation aircraft. Boeing embraced a visible mechanical solution to tackle airport noise. Airbus instead prioritized improvements inside the nacelle and engine architecture itself, reducing noise without altering external exhaust geometry. High-bypass turbofan engines already produce significantly less noise than older designs because more thrust comes from slower-moving bypass airflow rather than the high-velocity exhaust core. Airbus engineers concluded they could meet regulatory requirements without introducing additional drag-inducing structures into the exhaust stream. The clearest evidence that Boeing recognized the limitations of chevrons emerged during the development of the Boeing 777X and its GE9X engines. Despite the feature appearing prominently on the 787, 7478 and 737 MAX, Boeing abandoned chevrons entirely for its newest flagship widebody. Instead, Boeing and General Electric developed a radically different nozzle architecture using ceramic matrix composites, or CMCs. The result achieved a similar acoustic performance while reducing drag and weight simultaneously. GE9X Chief Project Engineer Terry Beeshold explained that the new nozzle technology provides equivalent cabin and community noise levels, but with lower drag and lighter construction. This transition is significant because it effectively acknowledges the trade-offs associated with chevrons. If the technology represented the optimal long-term solution, Boeing likely would have retained it on the 777X. Instead, the company invested heavily in eliminating the feature while preserving its acoustic benefits. Modern aerospace engineering increasingly favors integrated aerodynamic efficiency over external add-on solutions. Advanced materials, computational fluid dynamics, and improved nacelle shaping now allow manufacturers to address noise problems more elegantly than was possible when chevrons first emerged. Despite their drawbacks, chevrons were not necessarily a mistake, particularly on the Dreamliner. Boeing found a secondary advantage that partially offset the performance penalty and made the overall trade-off more acceptable for that aircraft specifically. Because the engines were substantially quieter externally, Boeing was able to reduce the amount of sound insulation material installed throughout the fuselage. Reports indicate the company eliminated up to 600 pounds, or roughly 272 kilograms of acoustic installation, compared with what otherwise might have been required. That weight reduction improved fuel efficiency and helped compensate for the thrust and drag penalties created by the chevrons themselves. The Dreamliner's broader design philosophy also supported the decision. Boeing engineered the aircraft around aggressive efficiency goals using composite materials, advanced aerodynamics, and next-generation engines. The equation was less favorable on smaller aircraft such as the 737 MAX. Narrow-body jets generally lack the same opportunities for large-scale insulation weight savings, while their high cycle utilization amplifies fuel burn penalties over time. The problem was never that chevrons failed technically. The issue was that they solved one problem while creating another. Boeing's use of engine chevrons on the 737 MAX, 747-8 and 787 Dreamliner represents one of the more unusual engineering compromises in modern commercial aviation. Developed alongside NASA and General Electric to reduce airport noise, the serrated nozzle design successfully lowered acoustic output by improving exhaust flow mixing. Yet the same vortices responsible for quieter operations also introduced drag and reduced engine efficiency throughout every phase of flight. That trade-off created a challenge virtually unique among major modern airliners because Airbus rejected the concept entirely, preferring alternative acoustic technologies that avoided continuous performance penalties. Chevrons solved a real operational problem during a critical period in commercial aviation development, but over time, advances in engine and materials technology revealed that quieter aircraft did not necessarily require permanent aerodynamic compromises. What do you think? Was Boeing right to prioritize quieter operations with chevrons, or do you think Airbus made the better long-term decision by focusing on engine efficiency instead? Let us know by leaving a comment, and don't forget to subscribe for more aviation content. See you next time. In addition to our daily YouTube videos, Simple Flying publishes over 150 articles and a podcast every week. Visit simpleflying.com.